So just like there are double integrals, in rectangular coordinates. So you might have like double integral over region D of the function f. Maybe the order is dx dy, maybe the order is dy dx. Let's not worry about it. Oh yeah, let's get both of those in there, right? So then, or the double integral over a region called D of the function f dy dx. And these integrals, which, they might be, which are hard maybe to evaluate or tedious to evaluate, but are nice in polar, right? So to integrate over the same region D, f, but now you have an r dr d theta to replace the dx dy. Similarly, in the same way, some triple integrals are nicer in cylindrical coordinates. Now previously, we had a picture like this, which allowed us to convert between rectangular and polar coordinates. So you might have a certain point, an x-coordinate there on the x-axis, y-coordinate there. You might have this point here, and we'd have, let's say, so based on where this point is located, there's this angle theta. This distance here was r, right? So from the picture, we would have x is equal to r cosine theta, y was equal to r times sine of theta. Just as a reminder of some things in polar coordinates, for instance, just some polar graphing, right? For some examples, r is equal to 2 would be the set of all points of radius 2, distance 2 away from the origin. And just as another example, we could have here a picture of theta is equal to pi over 4. And so what would that look like with the x and y axes drawn? This angle of pi over 4 or 45 degrees here. So you'd have all these points, sure, but you'd actually have all these points back here too. So you have these points because of r greater than 0, and then you get these points down here because of r less than 0. Let's go back up to this point and just make sure to label that this is the point xy in rectangular coordinates, or r theta in polar coordinates. Now what we're going to do, though, is we're going to borrow basically all of the work we have from polar coordinates and do this in three-dimensional space. I'm going to try to draw this picture. However, draw it flat in three-dimensional. It would look something like this. X-axis, y-axis, say a z-axis right here. And what I'd like to do is maybe pick, let me just sort of start by drawing this. So I've got this point that was just drawn thick here is in the xy plane. So you have this x value called x, you have this y value called y. I've just selected the angle here, theta. That's the same as selecting the angle up here. And the distance from the origin down to this point down here on the xy plane is going to be called r. So this is exactly the same as the r that's up there in the polar picture. But then what we'll do from here is we will go up a certain distance. And how far do we go up? Well, let's do that dotted. Okay, we'll go up a certain distance. So this dotted line that's being drawn is completely parallel to the z-axis. And how far do we go up? Well, this is just based on how far we select a z value here. So then we're going to have this point. And while this point in rectangular coordinates would be x, y, z, this point now is also going to be described as r theta comma theta comma z. The key point here is to make sure that theta is an angle in the xy plane only. R is also a distance in the xy plane. Okay, that I actually I'm looking at my own notes and I just want to emphasize again really here. Note, this is really the key thing. R is the distance in the xy plane only. Okay, so let's see. So now what's our conversion? We've got x is equal to r cosine theta as before. Okay, that you can see that from the picture down here. Y is equal to r sine theta. And z from the rectangular coordinates becomes z in these new cylindrical coordinates. So there's nothing really changed there. The z value is just as it was before.